Footstep Parameterized Motion Blending using Barycentric coordinates. We present a real-time locomotion system for animated characters to follow footstep trajectories for a large variety of human walking and running styles. During an offline analysis, we extract animation steps from a small database of motion capture clips. For both left and right supporting feet, we calculate the point cloud of foot landing positions. Each foot landing represents a vertex in the Delaunay triangulation. Considering the route in place, we have one triangulation for each foot. During runtime, we calculate the triangle containing any given foot landing position. The vertices of the triangle represent the landing positions for the 3 animation steps selected. We start by aligning the triangulation with the character's route position and orientation. Given a goal landing position, we calculate the barycentric coordinates of this point for the triangle containing it. This interpolation only considers foot position, so if we want to incorporate route velocity, we need to include the results of the polar band interpolator. We now have a new set of animation selected based on route velocity, and the resulting foot landing from the interpolation between them. For the 3 animations with highest weight selected based on route velocity, we check whether we can replace any vertex of the triangle and obtain a new triangle that still contains the goal position. The final blending is a trade-off between route velocity and foot accuracy based on a user input parameter, lambda4. In these results we can see a slow-motion sequence of a character following a handmade footstep trajectory. Each feet has its own triangulation, and we switch between them as the character reaches a landing position. Using only the polar band interpolator, we can follow route velocity trajectories, but the character is unable of steeping correctly in the desired positions. Interpolation based on barycentric coordinates can closely follow the desired landing positions. We can now simulate different gaits and distances between the feet while walking or running. The height of the red cylinders show the small offset between the result of a linear interpolation with barycentric coordinates, and the spherical linear interpolation over the joints of the skeleton. We can further adjust the landing position through a simple analytical IK solver. This allows us to also handle uneven terrain and correct foot orientation. The input parameter, lambda4, determines the trade-off between following footsteps accurately, when lambda4 equals 0, and simply following route movement when lambda4 equals 1. As lambda4 increases, it is more difficult to find a solution that guarantees correct foot landing. In this videos the character turns red in those circumstances. When lambda4 equals 1, the system performs polar gradient band interpolation based on route velocities. As lambda4 decreases back to 0, the agent can slowly recover and land its feet over the footsteps again. This video shows a character following a user-authored footstep trajectory. The quality of the results depends strongly on the quality of the clips available from the motion capture library. Areas with denser sampling of example steps will provide more accurate results. As can be seen in the video, the least precise movements in our results are side steps and back steps. This is due to 2 reasons. 1. We had a small number of animations compared to other walking gaits, and thus triangles covering that space have larger areas, and 2. Interpolation artifacts appear when blending between animations that move in opposite directions, for example a backwards step with a forward step. Increasing the number of animation steps for this area would improve the final results. The user can manually edit trajectories, We can handle uneven terrain. We can solve the original stepping stone problem for groups of agents in real time. We can handle over 60 agents in real time, each one following his own footstep trajectory. Agents exhibit diversity of locomotion styles based on footstep trajectories and the motion clips available. Here is an example of a simulation with over 100 agents at interactive rates following the output trajectories of a crowd simulator.